Good afternoon and welcome to our second REALISE webinar titled Deep Decarbonisation for Refineries Starts in Ireland, introducing the REALISE pilot campaigns. Before you get started, I would like to go over a few items so you know how to participate in today's event. Next slide, please. You have joined the presentation using your computer speaker system by default. If you have connection issues and would prefer to join over the telephone, just select phone call in the audio pane and the dial-in information will be displayed. Next slide, please. You will have the opportunity to submit text questions to today's presenters by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. This webinar will be recorded and you can watch it back on our website, realisecus.eu. Next slide, please. Hello, everybody. I'm Peter van Os. I work as a project manager at TNO in the Netherlands, and I'm the work package leader of work package 2 in REALISE. Next slide, please. I will present to you also the agenda of today. So I, as work package leader of work package 2, will give you a short introduction of the REALISE project, which is coordinated by Ina Kim from SINTEF. Then we will start with the presentation from Juliana Monteiro, also from TNO, about solvent testing in a real-life refinery setting. And then we have two presentations about the demonstration work in REALISE. The first one will be from Irving Skylogianni from TNO, demonstration at Irving Oil Whitegate Refinery, where we have also a premiere of our video introducing the test site and the test equipment. And then as last, we have a presentation from Thor Mejdell from SINTEF about the demonstration goals as SINTEF Tiller CO2 Labs, a presentation about the Tiller pilot plant. All presentations will take around 50 minutes, and then we have 50 minutes left for the questions and answers at the end of this webinar. I will now give a short introduction of the project. Next slide, please. So the REALISE project is all about to do a demonstration and a refinery of a CCUS, full CCUS chain to enable a quick implementation of CCUS at refineries. Next slide, please. The project runs from May 2021, so we're already on the way for more than a year, and it will run until the October of 2023. So it's a 3.5-year project, and we requested and got a 6-month extension because we were also affected by the COVID pandemic for the last 20 months. So we have a few delays, but we are catching up now quickly. And hopefully we are able to do all our work in the next period until October 2023. There are a few topics that we address in this project. The first one is CO2 capture with second-generation solvents. We're going to do a test with a mobile pilot plant on a refinery for a long period, the Irving refinery in Ireland. And we're going to use the solvent of that test, the used solvent for the test, also in a pilot in SINTEF, the Tiller pilot, where you see a picture from in the bulb above the square. We will have a look at especially at solvent management technologies, because I think it's one of the first of a kind that we have such a long test at different stacks at the refinery. So you want to look at solvent loss and also the control of emissions. And because it's a full chain project, we also look at CO2 transport, conversion and storage. All those three aspects will be considered in this project. And there's a strong focus on the Cork cluster in Ireland for this work. And last but not least, we also have a work package on the socio-political context of the CO2 capture on refineries, where we look also at public perception and things like that play a big role, I think, in the acceptance of CCUS in general, and especially also on refineries, of course. And then we have three business cases actually. So we have the business case at the Cork cluster in Ireland, And we also have 2 business cases in China and South Korea, which is really another environment, of course, and when other topics play a role. So I think it's really interesting to follow also that, to see how the business cases in these different countries can be assessed. And of course, we have a big work package also on dissemination and knowledge sharing. And we like to disseminate the results of this important project and to share it with the world. And so we will be active in webinars like this on our website, realisecus.eu, but also on various conferences. And on the right-hand side, you will see an overview of the partners in the project. So I think we have a very good mix of research institutes, industry in the project to make this project happen. And we have, I think, quite a strong advisory board also linked to the project. And we have regular meetings with the advisory board to get some feedback of the work we are doing and the approach we are taking. Next slide, please. So the REALISE objectives, they have been divided over a couple of work packages that you see depicted here on the right side. But the real objective is to also decrease the energy amount of CO2 capture by 30% by applying a new solvent. And I now don't see my slides anymore, so let me and maximize the use of a solvent by applying a good solvent management strategy. Also look at the yeah, thank you. Also look at to decrease the capex by 50% by using plastic as a building component for CO2 capture plants, and also lowering the capture cost by 30% by coupling the facilities with the power sector. And of course, we will provide guidance for the choice of CO2 capture scenarios at different refineries using an open access simulation tool. So we're also going to build a simulation tool where you can easily simulate, for instance, your industrial site and see how you can easily build up your CO2 capture infrastructure. Next slide, please. And this is then an overview of the case studies in REALISE. So we're going to look at the route for CO2 to chemicals, so the CO2 utilization part, and yeah, at the different business cases we defined in Ireland, South Korea, and in China. We're going to look at the various aspects also from CO2 to EOR and also CO2 transport and storage to depleted fields under the sea. And I think that is about what my introduction was. So I now like to introduce Juliana Monteiro, who will give the next presentation on this webinar. So Juliana, go ahead.
Thank you, Peter. I'm Juliana Monteiro, working as a scientist at TNO, and I'll be talking a little bit about solvent testing in a real-life refinery setting. So next slide, please. So basically, this presentation is an introduction with the aim of answering the questions of why do we perform solvent testing at first, and then why to do this at a refinery. So this is a presentation that will then serve as an introduction to the presentation from my colleague Eirini, who will talk then about specifically the demonstrations in the Irving Oil Whitegate Refinery. Next slide, please. So starting with why do we perform solvent testing? Next slide. So we're working with solvent-based CO2 capture, and this is a relatively mature technology. So depending on which solvent we're talking about and which application, it had already achieved TRL 9, meaning it's already commercially available and applicable. There are more than 10 technology providers in the market with proprietary solvents. And there are also open solvents, like for instance 38% monoethanolamine, which is known by MEA, and also other mixtures like CISA-1, which is a mixture of 2 different amines. So there are solutions already out there that can be used for capturing CO2 from flue gases from different industries. Next slide, please. In the REALISE project, we look into the possibility of adding another mixture to the list of open solvents. This mixture is given the name of HS3, but it's an open mixture. You can see the formulation of it here. And the idea is really to increase the number of choices that there are available. And as Peter mentioned, we have quite some interesting objectives to achieve within REALISE with lowering costs of CO2 capture, particularly for refineries. And we intend to do that by further developing this novel Solvent technology. Next slide, please. So when we talk about open solvent technologies, MEA and CISA-1, I presented the compositions in the previous slide, but these are the solvents that we have to look into. MEA is the first generation solvent. It has a relatively high energy demand and also relatively high amine consumption due to both degradation and volatile emissions. Solvents like CISA-1 were developed with the aim of lowering this energy demand. And we can see that for CISA-1, the demand is relatively lower than for MEA. And also, it's more resistant to degradation. So also the amine consumption is lower than MEA. And this is something that is still under further evaluation and development. So I didn't really put a number in here, but we already know that the consumption is quite lower than MEA. But one of the challenges with CISA-1 solvent is that it uses piperazine, which is amine that reacts really fast with CO2. It's a really good amine when it comes to capturing CO2, but it leads to issues from an HSC perspective. So it has some carcinogenic features that are not ideal, of course, and therefore there's room for improvement also from an HSC perspective. But in general, we always look into further lowering the energy demands and also amine consumptions. So those are the targets for the development of the HS3 solvent within REALISE. Next slide, please. So with aims of lowering the energy demand, lowering the emissions and the solvent degradation, we do different testing with the solvent, starting from acquiring lab data to characterize these different characteristics of the solvent. We then propose models to describe the functioning of the solvent, and we generate also pilot scale data, which Eirini and Thor will be talking about later on today. And we can use then this pilot scale data to validate models, and then use these validated models to perform full-scale simulations to really know how the solvent, and particularly HS3 solvent in the case of REALISE, will perform at full scale. So then we have more confidence in the type of cost data and design data that we generate. Next slide, please. So basically, we know why we want to perform this test, but then why do we want to go to the refinery to actually perform this tests? Next slide, please. So a refinery has multiple stacks. We can be talking about more than 10 stacks depending on the refinery itself. And these stacks have varying gas compositions when it comes to CO2 content, but also different impurities that can be present in the gas. And exposing the solvent to the impurities in long-term tests will allow us to evaluate degradation, which is one of the things that we want to lower, is the degradation rate of the solvent. So it's really important that we can evaluate degradation in a realistic environment with the presence of these impurities from the different stacks. So that this is one of the main reasons why we go on site. With the solvent being exposed to these impurities and in the real flue gases, we can then identify and quantify the products that are being formed during these tests. Next slide, please. Because we are doing this test with a realistic environment and we have realistic degradation, we also have the opportunity, and we will also do this within REALISE, to test degradation countermeasures. Next slide, please. And then finally, we can verify the impact of aging over the solvent behavior things like emissions and viscosity. How does this evolve over time? And then we can have a really good picture of what could be the expected solvent life. And this allows us to have a better cost estimate over the lifetime operation of a full-scale plant. Next slide, please. So just to summarize then, why do we perform solvents at the refinery? We really want to add this data that we observe on the pilot scale regarding which degradation products are formed, how does the emissions evolve, and how we can mitigate degradation. And we want to bring this information to the design of the full-scale plant for our simulations, so that we can have improved cost estimates, increased confidence in the model results that we'll have from this project, but we can also de-risk the scale up by exposing the solvents to realistic impurities. Next slide, please. So that was it from myself, and I would like to introduce my colleague Eirini Skylogianni.
Thank you very much, Juliana. I am Irini Skylogianni, and I work as a researcher in DNO. I have been heavily involved in the demonstrations activities within REALISE, and this is what I'm going to present you today, the preparations that we have done here in DNO for the demonstrations at Irving Oil Whitegate Refinery. I'm going to start by asking to show you a video that we have prepared. The video is aired for the first time here in the webinar, where you get a glimpse of what we have been working on. Please, let's see the video.
Hello, come to see the inside. So here we are inside the ATEX container with our main plant. ATEX stands for atmospheric explosive, and it is the name of a protection system when you want to operate in a potentially explosive environment. So within REALISE, we are going to capture CO2 in a refinery with a pilot plant, and therefore we needed to conform with the ATEX regulations. What you see here is the mini plant, our pilot. You can see the columns, the absorption column and the desorption column, and this is currently being modified to allow for optimum operations when we're ready. So what we're going to do there is that the flue gas from different stacks from the refinery will come through from this flange and then go through inside the columns where CO2 is going to be captured using solvent technology. So if you wonder how this container is becoming ATEX compliant, this is actually through positive pressure. So how it is going to work is that constantly we are going to get clean air from a non-hazardous area of the refinery that is going to be blown in with these fans, always in the upward flow until the top floor where we have the ventilation grating. We are going to get the power externally, and it will come here, and this is the power control cabinet. We are now on the second floor, and what you see here is the top of the columns. This is the top of the stripper, and of course the absorber that goes all the way up to the third floor. And here we are on the third and last floor, where you can actually see the top of our tallest column, the absorber. This is where the clean gas is going to come out, and it's going to be directed outside the container. This is the ventilation grating, and here there's going to be a flow controller in order to ensure that there is always airflow, keeping the atmosphere inside the container safe.
That was it for now, but stay tuned, much more is coming. Goodbye. So this was the video. Let's continue with the slides. Next slide, please. So the objective of this work is, of course, to demonstrate CO2 capture from Irving Oil Whitegate Refinery stacks using the HS3 solvent that has been developed within REALISE. Sub-objectives have been to modify TNO's mini plant for operation in a refinery, as you saw in the video, test the performance of the solvent with focus on solvent stability and emission mitigation, but also demonstrate solvent management technologies, such as technologies for the removal of oxygen and for iron. Next slide, please. If we want to see how the TNO's mini plant looks like outside this container, you can see it here in the picture on the right. It is a plant with a capture capacity of 25 kilos CO2 per day, and it allows for continuous cyclic operation. It is automated and can be operated remotely and supports operation for 24/7. We're using water wash technology as an emission control strategy, and we are monitoring emissions online continuously as well. Both artificial and industrial flue gases can be used. Next slide, please. So for those who might not be very familiar with the process, here is a very simple schematic of it. Starting from the left to the right, we are first seeing a smaller column, which is what we call a quench. There we can remove some impurities and also regulate the temperature of the flue gas coming into the second part of the picture, which is the absorption column. In this column, the gas is moving upwards, coming in countercurrent contact with the solvent, which is coming from the top of the absorber moving downwards, and in which contact the CO2 is being removed. Then the solvent will continue from the bottom of the absorber to the desorber, where by means of heat is going to be regenerated and then reintroduced back to the absorber. This is also the process that we are having in the mini plant, with the difference that now, in order to better control and understand emissions, we have a water wash, which is the upper part of the absorber, but we also have it on the desorber side to better to control the emissions. Next slide, please. The areas where flammable and hazardous materials are processed, so for example in a refinery, are considered potentially explosive atmospheres. So for safety reasons, all equipment and rigs must be ATEX compliant. As you also saw in the video, ATEX stands for Atmosphere Explosive. It's a European Union directive that we need to comply with when working in such environments. And there are different approaches to make something ATEX. So for the mini plant, there were one approach would be to change the different parts of the equipment to ATEX equipment, or the approach that we followed to set the mini plant inside a container which then complies to the ATEX regulations. Clean air is blown inside the container, therefore introducing overpressure, and this is how the atmosphere inside the container remains safe. Next slide, please. Besides the preparations from the TNO side and modifications in our mini pilot, a lot of work has also been done at Irving Oil Whitegate Refinery in order to welcome the mini plant. So first of all, the refinery location was assessed in terms of where the mini plant should be placed. And after this decision was made, the work continued with more civil, mechanical, and electrical works. There has been a study to calculate the wind load, since this is a quite high construction. Also, in good collaboration and data exchange, the necessary foundation has been laid and the scaffolding. The mini plant, in order to operate, we need some water and air, and of course power. So these utilities are in place there. And of course, telecommunication is a very important aspect, since the mini plant will be remotely operated, and this communication channel now has been confirmed and tested. Next slide, please. Flue gas characterization. It is important to know what the flue gas contains. So in the refinery in Ireland, there are 15 different emission points. So in order to evaluate which of them we are going to study in our work, we need also to measure and to know what these gases consist of. So it is important to know if there are any particles, because particles can form aerosols, therefore increasing emissions. SOx can form heat-stable salts, which will accumulate in the system and deactivate the solvent, leading therefore to a solvent performance reduction. NOx as well are important. Again, different degradation products and heat-stable salts can be formed, which can lead to the deterioration of the performance of the solvent. And of course, CO2, the most important gas to be removed, and this is the goal of REALISE. Next slide, please. Three main criteria were used for the selection of the stacks from which CO2 is going to be captured. So first of all, the CO2, of course. So stacks with the highest CO2 flow rates were prioritized, since those would have a higher impact. Secondly, the impurities, because since one of the sub-objectives of this work is to stress test this solvent, we wanted to have as much impurities as possible. Therefore, we chose the stacks also according to the concentrations of the different impurities, the SOx and the NOx that we expect to find there. Third, practical criteria, the distance from the mini plant location. It is not practical to choose stacks that are further away than 200 meters from the location of the mini plant. This is due to pressure drops and the requirement for additional blowers to manage to bring the flue gas to the mini plant. Based on this criteria, 6 stacks were selected, whose emissions combined account for 84% of the total CO2 emissions of the refinery. Next slide, please. HS3 testing. So based on the flue gas characterization of the selected stacks, the testing program of the HS3 solvent was drafted. Different parameters and settings were used in order to gain more insights on the mini plant operation with the solvent. The testing was performed using artificial gas here in the laboratories in Delft, And then we conducted 2 different campaigns, one with the lowest CO2 content that we expect to find in Ireland with 4.5 volume percent, and one with the highest CO2 content that we will find 10.5 volume percent in the flue gas. In each campaign, we varied the liquid to gas ratio and the stripping pressure in order to see the effect on the operation in terms of capture rate, solvent loading, temperature profiles, emissions, etc. Next slide, please. Having completed the solvent test, we are ready to start the demonstration program. As you can see in this figure, with the green color are noted the months and the overall duration of the operation of the TNO's ATEX pilot plant in Ireland. The total duration is 8 months, and then with the black lines you can see the change on the stacks. So we will study 6 different stacks. 5 of them will be studied in a short campaign of 4-week duration. Then we will change to the next stack, leaving for the end the longest 3-month duration study of a stack. It is expected that the work will be finished in August, after which the mini plant can come back to the Netherlands. Next slide, please. During the demonstration, TNO, Irving Oil Whitegate Refinery and SINTEF are going to collaborate closely. TNO, of course, is going to monitor and operate remotely the mini plant and conduct visits if needed. Irving Oil Whitegate Refinery will provide operators and the system engineers to perform the daily and weekly checks that are required for smooth operation of the mini plant. And then SINTEF, of course, will use their expertise to analyze the different solvent and water wash samples in a weekly basis so that we can study the degradation effects. In the end of this work, the technology with HS3 solvent will have reached TRL 6 to 7. We will have produced more data with which we can validate process models, and then these can be used as input for OPEX and CAPEX estimation for full-scale CO2 capture with HS3 solvent. Next slide, please. Thank you very much for your attention. Let's go now to the next presentation about the demonstrations in SINTEF.
Hello, everybody. My name is Thor Mejdell, and I'm a senior research scientist at SINTEF Industry in Trondheim. Next, and the title of my talk is the demonstration of campaigns at Tiller CO2 pilot plant. The main objective for this activity here is to demonstrate the benefits of using the HS3 solvent that has been formulated and optimized within the project. Important sub-objectives is to add a CO2 compression and liquefaction unit to the Tiller pilot. And then we will also test the performance of the HS3 solvent with focus on specific reboiler duty, how much energy per kilo CO2 captured, on solvent degradation, emissions to air, and then also impurities in the liquefied CO2. Finally, we will also demonstrate nonlinear model predictive control to minimize the energy consumption under fast changing operating conditions. Next slide, please. Here is the Tiller CO2 lab. You see the building to the left. It's located 10 kilometers from Trondheim city, and inside this 30-meter high building, we have the pilot plant. This building was completed in November 2009. Next slide, please. Here you see inside the tower, we have the absorber to the left and the desorber to the right. So both columns goes almost right up to the upper floor. Typical dimensions and features is that it can manage 100 to 350 cubic an hour. The liquid flow can be up to 20 kilo a minute. The reboiler is electrically heated and might have 60 kilowatt. And the CO2 out of the desorber can typically get up to 30-40 kilo an hour. And maybe one of the main things here is that it is very well equipped with measurements. We have, for instance, 160 temperature every meter in each of the columns. We have a lot of pressure sensor and flow sensor and analyzers and so on. Next slide, please. Here is the simplified flow diagram from the starting of this pilot. We have to the left the exhaust gas coming from either a propane burner that is heating the area at tiller, or a combined bio or coal burner. This might be mixed with diluted air and also, if needed, the recycled CO2 in order to get a composition that is suitable for our experiments. This gas goes into preconditioner, very much like what Eirini said about the TNO plant, and is then there cooled down to a desired humidity temperature, typically 35 to 40 degrees Celsius. Then you have a blower that blows the exhaust gas into the absorber column in 4 sections. And at the top, we have 2 stages with the water wash to prevent that amines are going out with the atmosphere. On the desorber side, we have 3 sections with there also 2 water washes that also will is for keeping the amines and amine degradation products down in the liquid. And then the CO2 is condensed and we can get the pure CO2 or 99%. This one will then go into the liquefaction unit that we are presently building. Next slide, please. We also have 2 additional water wash sections, which was installed some years after the first pilot. So totally, we can now use 4 water washes in series. Next slide, please. So for the main demonstration campaign, we plan for a 12-week campaign starting in September next year. And one of the ideas here is to mix some of the degraded liquid coming from Irving, such that also this plant will have some of the impurities that is typical for refineries. We will then mix this with some fresh solvent, and then we can say that it a kind of mimic partly reclaimed solvent. So since this column has full height, I will say we might get full separation in the column. We will use this plant in order to get specific reboiler duty measured in this plant. We will also then compare the result from this campaign from an earlier MEA campaign And we will measure emissions of the solvent and solvent degradation products to the air. As with the various process conditions. And the number of water washes, we have up to 4. And we will measure with using FDR in out of the gas out of the last wash, and also doing manual gas sampling. And finally, measure impurities in the sea product. And this also with various conditions, for instance, the water washes in the desorber column. Next slide, please. So this is also an important part of the campaign. We will use and demonstrate nonlinear model predictive control. It is a model, a schematic figure of this type of controller. You have the plant, and you have a dynamic model, and what you measure of both the disturbances and manipulated variables like valves and heat input and so. The dynamic model uses its model to predict the output, and we compare that with the plant, and then we can use an estimator to update also the model. So when the model is in good shape and reflect the plant well, then we can also start to optimize the future control variables. In our case, it will typically be the reboiler duty, the amount of energy to the reboiler, and the liquid circulation rate. So in the beginning of the campaign, we will start doing some step response, dynamic step response, just to see that the dynamic of the model is adequate. And in the last part of the campaign, we will have this nonlinear model predictor tested in closed loop, and then demonstrate the capability of this type of control to manage energy, minimize energy consumption under fast changing operating conditions. And both this model and the system will be give valuable data for the work package 3. Yeah, next slide, please. The main thing that is going on at the moment is the construction of the CO2 compression and liquefaction unit. This will use the CO2 flow directly from the desorber top. And the idea is to measure impurities both in the knockout water between each of the compressor stages, and also in the CO2 liquid going out from this unit. And then we will look at the impact of amine, degradation products, and so on, and also desorber water washes, how we run them. We hope during with this unit that at least in terms of impurities will be very similar to large-scale processes. And the end product in REALISE is transportation for ships, typically 16 bar and minus 27 degrees Celsius. And we will store the CO2 temporarily. Next slide, please. Yeah, so the background for all these compression and liquefaction units is that the purity requirement be quite restricted and can be quite different from different purposes. For, let's say, CO2 transport by ship or by pipe, for EOR or food industry, or not at least chemicals for the for the CCU, utilization of carbon capture. For instance, methanol synthesis. To the right, you can see a typical specification from the AGA that specify what is the requirement for beverages in the food industry. But you have the similar specification for the Northern Light and other storage and transport campaigns or projects. What we know is that the compound found in exhaust gas leaving the absorber also are present to some extent in the CO2 stream. And this includes amines and degradation products. So that is our main focus. Next slide, please. So here you see at PID of the compression and liquefaction plant. And the gas come from the absorber in the bottom of this PID. It goes first to a warm compressor, which is then cooled down after compression. The temperature goes up there, and the water afterwards will go to a knockout drum, which we can measure to see which of the impurities goes with the water and which is going further with the CO2. And then it goes to the second stage of compression and the third stage of compression before it is finally dried into the dryers, and then it will be cooled down to typically minus 5 degrees, and after that the pressure will be released to 15 bars, and the liquid will then also drop to minus 25. Next slide, please. So here you see the 3 compressors that SINTEF has invested in, and also this to the left, also the unit that will cool down and do the liquefaction when it is compressed. And to the right, you see a storage tank that we have bought from Linde. This unit will first be commissioned and tested for MEA. Next slide, please. Next, yeah, there, thank you. That's my last slide, and you see the guy standing there with the white helmet is Kai Jarbo, who is a researcher at SINTEF and has been the main person for both design and selecting equipment. Thank you very much for your attention.
Yes, okay, thanks a lot, Thor. I also want to thank all the other presenters for their presentations and for Irrini for showing us the ATEX container that will be placed in Ireland in the movie. So we're now going to begin answering the questions submitted during today's presentations and start the discussions. We already have a few questions on the list, and as a reminder, you can still submit your questions through the questions pane in your attendee control panel. And yeah, questions won't be lost. So if we don't have enough time to answer all the questions, we'll pick that up later and answer you for your questions that you submit during this webinar. So I would like to ask all the presenters to switch on their camera, and then we can kick off the Q&A session. Yes, there you are. Good. So I think Juliana was the first, so I will pose the first questions to Juliana. Yeah, you talked about lowering the energy demand with the new HSV solvent. How realistic is it to lower the energy demand of new solvents in general? I mean, is there a lower limit, and how close can we get to this lower limit?
That is indeed a very good question. Yes, that there is a lower limit that is set by thermodynamics, basically. So the minimum amount of energy that we have to put into the system to separate the CO2 from the other molecules in the gas. So that's the minimum energy that we can give, that we have to give to the system. And of course, every process has inefficiencies associated to it and energy losses. So when we look at, for instance, MEA, that I showed some numbers in there, that's the first generation solvent that gives typically from 3 to 3.5 gigajoules per ton of CO2 captured. That's the energy that you can that you have to input in there. And there was already a lot of work done on lowering these emissions. And in the second generation solvent system like CESA1, we're down to 2.2, 2.6, depends on also the CO2 content in the gas. So with this second generation solvent systems, we are already close to something like 50% efficiency of the process regarding this minimum energy required by thermodynamics. And so a lot of chemical engineering processes work with lower efficiencies than that. So we are already quite close to this thermodynamic minimum from this perspective, and it's really hard to lower it even further. So what we intend to do with HS3 is to get close to this mark of CESA1 with this relatively high efficiency there, and then improve on other aspects related to the HSE, so particularly the aspects of the solvent not being carcinogenic, for instance, and aspects such as degradation and emissions also are important. So basically the full package has to be addressed, but it's relatively hard to, with aqueous solutions of amines, to further lower this emission requirements.
Yeah. Okay. Yeah. Thanks, Juliana, for this answer. I also have a question for Eirini. How would the cooperation between Irving, the people at Irving and TNO go? Will you have operators from TNO on site, or how is the control of the mini plant organized?
Yes, thank you for the question. The operators of TNO are not going to be in Ireland during this whole campaign, but our pilot can be operated remotely, and it is fully automated, can be operated 24/7. So our operators from here, from the Netherlands, are going to be following up, and then doing specific intervention, and of course ask for help from the people that are there if necessary. What it is expected from the operators and the engineers in the Irving Whitegate Refinery is to do some daily or even weekly checks. For example, taking the samples. We're using a lot of water baths, so in order to maintain the water balance in the plant, we need to meet the inlet gas temperature to be the same as the outlet from the top of the absorber with the washes. So for the water washes, we use baths, and obviously some water will evaporate, someone will have to fill it in. So this kind of daily and weekly tasks are going to be performed in Ireland.
Okay, thank you. Nice that you can operate it indeed online. I think here's a question for Thor. Thor, you mentioned in your presentation that you're gonna mix the fresh solvents with some solvent from the plant in Ireland to have a start of degradation. How representative is it then? How degraded is it then when you put in this 20 liters? Is it then minimum degraded or medium, or what do you think? I can't hear you.
There?
Yes, this is good.
Yeah, okay. Sorry for that. Yes, I mean, this is something that we really don't know. So this will be what it will be. So also this will depend, of course, of how many operating conditions that will be performed in at Irving, and a lot of variables that is difficult to see, but to know in advance. But we will typically start with the fresh one, and then add the degraded one to the solvent. So we can at least compare the performance of the degraded and the fresh one. That is also an interesting number and information.
Okay, thanks. I have here also a bit more general question, so I will pose that to Juliana. Do you think that post-combustion carbon capture with the HS3 solvent will be more or less economic than pre-combustion capture, for instance, with hydrogen firing for the case of refineries?
Yeah, that's a good question. I think it's a bit hard to answer. So in general, I think the solvent-based technology can be competitive with pre-combustion for refineries. When it comes to the HS3 solvent, what we intend to achieve is to lower the costs by 30%. So that's of course a major achievement if we actually manage to do that, and that comes from both capex and opex reductions. So I think it all depends on it's not only the fact that we use the HS3 solvent, but how we are intending to integrate CO2 capture with the different stacks in the refinery. So it's really the whole strategy of the REALISE project to capture CO2 from all the different stacks and integrate the solvent and have a centralized stripper. And from that perspective, if we actually manage to do this and to show that this can work in a full-scale refinery system with the 3 different use cases that we will evaluate in the project, then I assume that this is more cost-effective than pre-combustion. Yeah, well, remains to be seen. I think that's and of course in the project we will not evaluate pre-combustion per se, so we will then focus on the post-combustion, but then it would be an interesting study then to compare the different technologies in a future project, I think.
Yeah, okay, thank you. I think a short question for Thor. The nonlinear model predictive control system, will that be actually used at the trial at Tiller? So do you have the hardware and software to really operate it at the plant?
Yes,
Okay.
we will in closed loop. So this will communicate with our control system and send set points to different parts of the plant.
Yeah. Okay. Good. I think we have 2 minutes to go, so I have maybe at least the last questions for Irrini. You showed the schedule for the shorter and longer and the one longer campaign for the different stacks of at the Irving refinery. Is there a special method to select which stack will get the largest campaign, or do you use some kind of, what knowledge do you use to select the stack for the longer campaign?
For the longer campaign, we have decided to all these criteria that I showed you in the presentation, of course, are present for all of them. And then we decided to have the longest campaign for the stack that has the highest CO2 concentration, actually.
Okay.
This is the decision that has been made. Yeah.
Yeah. Okay. Thank you. Okay, I think we're spot on time, so I think we have come to the end of our webinar. The questions that are not answered will be answered by email. So I'd like to thank everybody for attending today, and of course the presentators and the organizers for making this webinar possible. And yeah, once you leave today's sessions, you will receive a survey on the presentation, and we would appreciate if you would complete that and provide your feedback that we can use in future webinars. So you will receive a follow-up email within 24 or 48 hours with a link to also to view the recording of today's webinar. You can use it also for your colleagues. So on behalf of all the presenters and myself, I would like to thank you for joining us today, and have a great rest of your day. Thank you very much.